glad to be here. Thank you so much to the Southern California our user group for having me. I am really happy to be here talking specifically about feature engineering for text data, and that's for a couple of reasons. So having a better understanding of what it is we do to text data to make it appropriate as input for machine learning algorithms has a lot of benefits. Of course, if you are directly getting ready to train a model, then this is something you need to know how to do. But also, if you're at the beginning of a text analysis project and you're not sure if you're going to head towards training a model or not, knowing the kinds of transformations that are often used for text modeling can be super valuable as you go even at the beginning of the EDA processes. Um, or let's say you're trying to understand the behavior of a model that you're interacting with in some way. Understanding how text was processed in order to get it ready for the model can help you understand the behavior of the model if you're using its output in some way. So when we build models for text, either supervised ones or unsupervised, we start with something that looks like this. So this is some example data I'm going to use a couple of times during this talk. And so it's data that describes animals. And then we have, some information, some other information. Let's imagine we have other information as well. Like I think in this little example data set, it's about the diet. Thank you to Emil for preparing this data set in some of his work. So this looks familiar to me and to you as speakers and writers of human language. Like we're familiar with language as it is represented like this. And we can, as English speakers, we can parse it, we can read it out loud, we could say these kinds of things to other people. So this kind of data is being generated all the time in all kinds of contexts. So, I bet no matter what context you work in, what kind of work you do, you probably have observed this either directly or kind of one level removed from you. Text data is being generated by survey takers, by electronic health records, by social media. However, computers aren't great at doing math on language that is represented like this. So instead, language has to be dramatically transformed to a machine-readable numeric representation that's more like this one that I'm showing right here to be ready for computation for almost any kind of model. So I spent a fair amount of time working on software for people to do exploratory data analysis, visualization, summarization, and so forth with text data in a tidy format. And I'm a big believer in the flexibility and all the benefits we get from using tidy data principles when it comes to even text data. But when it comes time to build a model, when it comes time to use some kind of machine learning algorithm, what the underlying mathematical implementation needs is usually something that looks like this. So this is a way to look at a document term matrix. So on each row is a document, say like a description of an animal. Each column, it represents a token, a word here, and we have counts here that says how many times each document uses each word. So it's called a document term matrix. So the exact representation might differ from what I've shown right here. You might weight by something called TF-IDF instead of counts, or you might keep sequence information like we often want to when we're using deep learning models. But for basically all text modeling, from simpler models like naive Bayes to word embeddings to anything that's state of the art today, like transformers, we have to heavily feature engineer and process language to get it to a representation that's suitable for machine learning algorithms. So, in my day job, I work on an open source framework in R for modeling and machine learning that's called Tidy Models. And a lot of the examples that I'll be showing today use Tidy Models code. Some of the specific goals of the Tidy Models project are to provide a consistent, flexible framework for real-world modeling practitioners, from those who are beginning and just starting out to those who are very experienced. I'd say the second one is to harmonize the heterogeneous interfaces that we have in modeling in R. So you only have to learn one time how to do something instead of learning over and over and over how to do very similar things. And also to encourage good statistical practice by the design of functions, documentation, books. So I'm glad to get to show some of what I work on and build and how it applies to text modeling. But a lot of what we'll talk about today isn't really that specific to tidy models or even to R. It's a bit higher level. Like, we're going to focus on these basics of how is it that we transform text into predictors for machine learning. So Tidy Models is a meta package in a similar way that the tidyverse is. So if you've ever typed library tidyverse and then you've used, ggplot2 for visualization and dplyr for data manipulation and tidyr for data reshaping, Tidy Models works quite similarly in that, you can attach this meta package, and then it attaches a set of packages, each of which has a different focus. So pre-processing or feature engineering, what I'm talking about this evening, is part of a broader model process. I would argue it starts really with EDA, like exploratory data analysis steps, and then it comes to completion. You could maybe ask questions about when are you done with a model, but let's say you're done with the model after you evaluate it. Let's say that. So Tidy Models as a piece of software is made up of these R packages, each of which has a specific focus, like resampling data. The R sample package will create cross-validation folds, bootstrap folds, will split your data for you. Or there's a package for hyperparameter tuning. It has the name Tune, one of these packages is for feature engineering. And the name of the one that is for feature engineering or data preprocessing is recipes. So in Tidy Models, we capture data preprocessing and feature engineering in the concept of a preprocessing recipe that has steps. So you choose what variables or ingredients you're going to use. You define the steps that you want to carry out, and then you prepare them using training data. So this is the point at which we learn the transformations that we want to carry out from the training data that we have. And then we can apply it to any other data set, like testing data, during the process of training a model, or new data at prediction time, once we have taken the model and say, put it in production and want to apply it to new data that comes in. So these variables or ingredients that we use in modeling come in all kinds of shapes and sizes, and that includes text data. So some of the techniques and approaches that we use for preprocessing text data are the same as what you might do for any other kind of data that you might have. But some of what you need to know to be able to do a good job in this process for text is different and is specific to the nature of language data. So I have written a book with my co-author, Emil, who is here as one of the organizers. And so this book is about supervised machine learning for text analysis. And actually the first third of the book focuses on how we transform natural language into features that we can use for modeling. So the middle section is about how to use these features that we create in what you might consider more traditional or simpler machine learning models, like regularized regression, support vector machines, and other types of classical statistical modeling that tends to work well with text data. The last third talks about how we use deep learning models with text data. So deep learning models still require these kinds of transformations from natural language to a mathematical representation, but they are often able to inherently learn some of these structures or features that we have in the text. So this book is now complete. It's available. You can buy it. People have print copies, but it's also available in its entirety at smalltar.com. So if you're new to dealing with text data, understanding these fundamental approaches for text set you up for being able to train effective models. If you're really experienced with text data, you've used it a lot. You've probably noticed, like we did, that the existing literature is pretty sparse when it comes to a detailed, thoughtful exploration of how do these pre-processing steps work, and how do the choices that we make there impact our model output. So let's dig into that. And talk about these kinds of transformations that we have. So typically, one of the very first steps in transformation from natural language to a machine learning feature, or actually any kind of text analysis, including EDA before you build a model. This typically the very first step is tokenization. So in tokenization, we take an input, like a string, and a token type, like some meaningful unit of text, like a word, and we split the input into pieces of tokens that correspond to the type. So probably the most common, most commonly, the meaningful unit or type of token that we might want to split text into units of is a word. So this might seem straightforward, but it turns out it's difficult to clearly define what a word is for many or even most languages. So many languages don't use white space between words at all. Even languages that do use white space, like English, often have particular examples that are ambiguous. And Romance languages like Italian and French use pronouns and negation words that may better be considered prefixes with a space. And then there's English contractions like didn't, which you may more accurately think of those as two words with no space. And so even when we're at just this very, very first step, this very what might seem like the simplest option, it turns out it's already complicated. Once you have tokenized text, it's on its way to being able to use in EDA, unsupervised algorithms, or as features for predictive modeling, like these results show here. So these results are from a regression model that's trained on descriptions of media from artwork in the Tate collection. And so we see here that artwork created using graphite, watercolor, and engraving, these are more likely to come from, to be created earlier, to come from older art that's in the Tate collection. And artwork that is created using photography, screen printing, and dung and glitter, this is more likely to be created later for more new or contemporary art. So the way that we tokenize the natural human-generated language that we started with, that was describing the medium for each piece, like what kind of art medium was used to create the artwork, the way that we tokenize has a big impact on what we learn from it. So if we tokenized in a different way, we would have gotten different results in terms of, probably in terms of performance, like how good a job did we do predicting the age of artwork, but also in how we interpret the model, like what we can learn for it. This first step of tokenizing impacts everything afterwards, everything that comes afterwards, and what we're able to, how we're able to predict and what we're able to learn. So another way we could have tokenized, another way to tokenize is instead of breaking up into single words or unigrams, we can tokenize to n-grams. So an n-gram is a continuous sequence of n items from a given sequence of text. So this shows that same example text describing our animal here divided up into bigrams or n-grams with 2 tokens. So notice how the words in the bigrams overlap so that collared appears in both of the first bigrams. So the collared peccary, peccary also referred. So n-gram tokenization slides along the text to create overlapping sets of tokens. This shows trigrams for the same text, so sets of 3 words. So using unigrams, like identifying them, is faster and more efficient, but then, we don't capture any information about word order. When you have, if you ever heard bag of words, that's where we divide everything up into just words, and then we just don't worry about order at all. We just like put it in a bag and shake it up and think about the words themselves without any information about order. So using a high value for n keeps more information. But the vector space of tokens increases dramatically. This corresponds to a reduction in counts, how many times we see each token. And depending on like your particular data set, you may not be able to get very good results once you sort of bump up n here. Combining different degrees of n-grams, like at the same time in the same analysis, can allow you to extract different levels of detail from text data. So unigrams tell you which individual words have been used a lot of times, and sometimes some of those words could possibly be overlooked in bigram or trigram counts if they don't co-appear with other words, the same other words often. So we've got all these options. How do we know what to do, and what kind of results do we get? So this plot compares model performance for a lasso regression model predicting the year of Supreme Court opinions with 3 different degrees of n-grams. So, only bigrams, bigrams and trigrams, only unigrams, unigrams and bigrams, and then unigrams, bigrams, and trigrams. So this comparison holds the number of tokens constant at 1,000. So here there is, we notice that the holding the number of tokens constant using unigrams actually performs best here for this particular corpus of Supreme Court opinions. So this is not always the case. It depends on the kind of model you use. It depends on the data set itself. You might see the best performance combining unigrams or bigrams, or some other option. This is a machine learning is a heuristic field, as a empirical field, and there's no way to know ahead of time what is going to work out best. So in this case, if we really wanted to incorporate the more complex information in bigrams or trigrams, we probably would need to increase the number of tokens quite considerably. And that may not work out depending on the data set that we have because of how much overall data we have. So keep in mind here that identifying n-grams is computationally expensive, especially compared to any improvement that you might see. Here we saw no improvement, to be clear, but you may in some other case, but that has to be weighed against the cost, the computational cost of identifying them. So in this particular data set, we did some benchmarking, and using bigrams plus unigrams takes more than twice as long to train as unigrams. This is, remember, for the same number of tokens. And adding in trigrams takes almost 5 times as long as training on unigrams alone. So it really bumps up there. So I see that question from Jeremy there, and like that's kind of the answer here. As like it depends so much on the individual data set you have, the model that you're using, that there truly is no way really of knowing ahead of time. I mean, you would probably want to try start with something like this, like one and two, 1 through 3, see how that goes. Like, don't just start off and be like, what am I going to try first? Order five, order 5 engrams, right? So something like this is reasonable, and often people find the best results from, one and two. If you have a ton of data, you might be able to get away with like 1 through 3 here. All right, so let's go the other direction. Let's go the other direction. We can tokenize. Tokenize to units that are smaller than words. So like these. These are called character shingles. So there are multiple different ways to break words up into subwords. That are appropriate for machine learning, and often these approaches or algorithms have the benefit of being able to encode unknown words that you didn't see during training at prediction time. So this kind of like using this kind of subword information is a way to incorporate like what are called morphological sequences into our models. So these are just words that are tokens that are just 3 characters long. But you can think of examples where if you go down to subwords, then you are able to uh, match things from your training set that you didn't actually see a whole word or unigram in training, but when it comes up in testing. So that let's look at the another example. So these results are for a classification model with a data set of very short text, super short. It's just the names of post offices in the United States. So the idea here was to identify which of the post offices are located in Hawaii and which are located in the whole rest of the United States. So I created features for the model that are subwords of these post office names. And here we end up learning that names that start with H or P or contain that ale subword are more likely to be in Hawaii. And on the flip side, subwords and, like land or that sort of subword, RI and ING, those are ones you're more likely to see outside of Hawaii. So this is an example of how we use different kinds of tokenization, and we can get out different different results when we build a model. So in tiny models, we collect all these kinds of decisions in about tokenization in code that looks like this. So we start with a recipe that specifies what ingredients or variables we're going to use, and then we define the pre-processing steps. So the here we can use say our first step is to tokenize, and so even at this very first and arguably basic or simple step, the choices that we make affect our modeling results in a big way. All right, so let's talk about another common early step that we might have. So once we have split text into tokens, we often find that not all words carry the same amount of information, if maybe any information at all, for some machine learning tasks that we want to do. So common words in a language that carry little or maybe no meaningful information are called stop words. So it's common advice and practice to remove stop words like these in this list for various NLP tasks. So what I'm showing here is the entirety of one of the shorter English stop words lists. It's one that's used really broadly. So you see here pronouns, conjunctions, these like glue words that keep that like make sentences work in English in this example, but that you look at them and you're like, I think those probably are not super meaningful. So you see this like common practice to just remove them, but that decision is often more involved and maybe more fraught than what you'll find reflected in a lot of resources that are out there. So almost all the time, real world NLP practitioners out there dealing with real data use pre-made stop word lists. So this plot visualizes set intersections for 3 common stop word lists in English in what is called an upset plot. So this kind of plot is called an upset plot. So the lengths of the bars, down there on the bottom show you the lengths of the 3 sets, and then the lengths of the bars show you the intersections, how much intersection there is. So notice a couple things. The lengths of the lists are quite different. And also notice they don't all contain the same sets of words. So people have found, for example, just plain old misspellings in some of these kinds of lists. But the really important thing to remember about stop word lexicons is that they're not created by some like perfect neutral setting, but instead they're context specific. They are created from large data sets of language. So, and because of that, it turns out they can be biased. So both of these things are true about stop words because these lists are created from large data sets of language. So they reflect the characteristics of the data that are used in their creation. So this is the list here of the 10 words that are in the SMART lexicon, but not the snowball lexicon. So notice they're all contractions, but that's not because the snowball lexicon doesn't include contractions. It actually has quite a lot. Also notice that this list here has that we see that list had he's, but it doesn't have she's. Notice that we've got pairs here, he'd, she'd, he'll, she'll. We have she's on the list, but we do not have he's. So this is an example. This is just like one tiny example of the kind of bias that occurs in these stop words, these lexicons of stop words. So picture how these things were created. So a lexicon creator, usually some kind of like computational linguist, or maybe someone like 70 years ago when people were still starting to use, computers with language, they would take a big data set and count up the words and look at the most frequent words in some big corpus of language that they had, and then make a cutoff. And then you have to make some decisions about where the cutoff is going to be, and what are you going to include and what are you going to exclude. And then you end up here, right? Because let's say your data set of language has more text in it about men than women. And so you decide wherever you make your cutoff, it turns out one of these contractions ends up in and one of them does not. So like so many decisions when it comes to modeling with language, we as practitioners have to decide what is appropriate to our particular domain. It turns out this is even true for picking a stop word list. So in tidy models, we can implement a pre-processing step like this one by adding an additional step to our recipe. So first we specified what variables we were going to use, then we tokenized the text, and now we're removing stop words. Here we're just removing a default set, but you can remove custom sets of stop words. You can take a set of stop words and customize it yourself to whatever is most appropriate to your use case. So this plot compares the model performance for that same data set of Supreme Court opinions with 3 different stop word lexicons of different lengths. So here the snowball lexicon contains the smallest number of words, and in this case it results in the best performance. So here removing fewer stop words results in the best performance. So this specific result is not generalizable to all data sets and contexts, but the fact that removing different sets of stop words can have quite noticeably different effects on your model results is quite transferable. And again, we're back to hear me saying again that like machine learning, predictive modeling is a largely empirical task, a largely heuristic task, and the only way to know what is going to work best with your data is to try several options and to use good statistical practices around resampling data so you have some confidence that you're not being fooled by the results that you're seeing. All right, let's talk about something that I think I saw someone ask up about a little bit ago, and that is stemming. So when we deal with text, often documents contain different versions of one base word, which we call the stem. So what if we don't think we're interested in the difference between animals plural and animal singular, and we want to treat them both together. So that idea is at the heart of stemming. So there is, again, no one right or correct way to stem text. So this plot shows 3 approaches for stemming, pretty, simple approaches for stemming, starting from literally just removing a final S to more complex rules. That middle one is a set of more complex rules about handling plural endings. It's called the S stemmer. And then that one over on the right is the probably, the best known implementation of stemming called the Porter algorithm. So if you look at these, you notice that Porter stemming is the most different from the other two. And this is just the top 20 words in this data set of animal descriptions, and notice how species is treated quite differently. Notice how animal is treated quite differently here. Notice what Porter stemming does to the word animal. Notice the combinations of live, living, life, lives, and how those things are handled differently by these different stemming algorithms. So practitioners typically are interested in stemming text data because it can bucket tokens together that belong together in a way that we understand it. So we can use these kinds of stemming rules, which are pretty like step by step. They're rules based, they're algorithmic in nature, like first do this, then do this, then do this, to like process and cut off the ends of words. Or you can use what's called lemmatization, and this is usually based on big dictionaries of words, and it incorporates not just sort of algorithmic chopping off of the ends, but actually it incorporates linguistic understanding of what words belong together by using big data sets of big dictionaries of words. Either way, it sounds like, hey, this is going to be a helpful thing to do when we have so many features, which is what happens when we have text data. So this is a matrix representation of text data. Just a little bit of like, let's create one and then let me tell you something about it, that much like we would use in a model. So look how many features there are, like almost 17,000 features, and look how sparse this is. The sparsity is very high. So think of this is the sparsity of the data that we'll want to use to learn to build a supervised machine learning model. So most documents don't contain most words, right? Like we don't have the examples of the words, the features we want to use in our machine learning model. We don't have them in most of our observations. Each observation uses different words, different tokens. So if we stem the words, like I'm doing here with the word stem function from the Snowball C package, we reduce the number of word features by many thousands. The sparsity didn't change as much, which just emphasizes here, I think, like how incredibly sparse this are. So common sense says that reducing the number of word features in our data set like this so dramatically that this is going to improve the performance of a machine learning model that we train with it. So, if we take out features that are not going to be important. But that does assume that we haven't lost any important information by stemming. So it turns out that stemming can be helpful for some data sets, for some kind of models, in some contexts. But typical stemming algorithms are somewhat aggressive, and they have been built to favor sensitivity or recall or the true positive rate. And that is at, let's see, that is at the expense of specificity or precision or the true negative rate. So in a supervised machine learning context, this affects, the model's positive predictive value, the ability to not incorrectly label true negatives as positive. I think I said that right. So stemming can increase a model's ability to find the positive examples, like say the animal descriptions associated with a certain diet, if that's what we're predicting. But if text is overstemmed, the resulting model loses its ability to label negative examples. So say the descriptions that are not about that diet, to label those correctly. So even quite basic preprocessing for text, like what is shown here in this feature engineering recipe, can be computationally expensive. And these choices that we make, like whether to remove stop words or to stem text, can have a dramatic impact on how machine learning models of all kinds perform. So what this means is that the prioritization that we as practitioners give to learning, teaching, and writing about these steps really contributes to like better, more robust statistical practice in our field. So I mentioned before, I showed you those matrices and their sparsity, right? And it was like 98% sparse, and it's quite common to end up with, document term matrices that are 99% sparse, like extremely sparse. So the sparsity of text data is one of the really defining characteristics of it. So because of how language works, we use a few words a lot of times, and then a lot of words just a couple of times. And so with a real set of natural language, you end up with relationships that look like this in terms of how sparsity changes as you add more documents and thus more unique words to a corpus. So sparsity goes up really, really fast as you add more unique words to a corpus. And that means that if you have to represent that, that matrix that we talked about in your computer, right? The memory that it takes goes up also a lot. Turns out this is true even if you use specialized data structures meant to store sparse data, like a sparse matrix where you don't keep track of all the zeros, you just keep track of where the elements are and what grows there. You still end up growing the memory required to handle a data set in a like really non-linear way. What this means is it can take a while to train a text model, even on fairly modestly sized data sets. So this has motivated this kind of noticing this just nature of language data, has motivated linguists to work on vector models for language. So vector models can reduce the number of dimensions that representing text data then you make that new set of vectors based on how people use language. People have been trying to do this for a very long time, building these vector models of language that are more dense instead of so extremely sparse. So this quote here dates to 1957, like before people were really, doing much machine learning. So these kinds of dense word vectors are often called word embeddings. So the idea here is that we use now, in modern day, we use statistical modeling of some kind, maybe just really straightforward word counts plus matrix factorization, or maybe fancy matrix factorization like that involves neural networks. So you use some kind of model to take this really high dimensional space and create a new lower dimensional space that is special because the new space is created based on these vectors that incorporate information about which words are used together. So you need quite a big data set of text to create or learn word embeddings. So like on the order of a couple million words, not unique words, but a couple million uses of words. So this table that I'm showing here is from a set of embeddings that I created using a corpus of complaints to the United States Consumer Financial Protection Bureau. So these are complaints from consumers about things like credit cards and mortgages and financial products like that. So in the new space, defined by the embeddings, the word month is closest to words like year, months, monthly, installments. Like these are payment, week. So these are the words so we had the super sparse, really high dimensional space. We learned a new lower dimensional space. And in that space, how far away words are from each other is related to how they're used in the corpus. So the word month is used in a similar way that the word year is used, similar to the way the word monthly is used, and installments. In this new space defined by these embeddings that I made from the complaints, the word error is closest to words like a mistake, clerical, glitch, errors, problem, miscommunication, and misunderstanding. Like these are the words that people are using in a similar way when they're talking about what went wrong with their mortgage or their credit card or their student loan payment. So you don't have to create embeddings yourself. If you don't have that enormous corpus where you can learn a reliable set of embeddings, you can use word embeddings that are pre-trained. And what this means is they were created by someone else based on a huge corpus of data that they have access to, and you probably don't, because maybe they're Google or Facebook or something like that. So this table shows the results for these same words, but now from the GLOVE embeddings. So the GLOVE embeddings are one of these pre-trained, one of these sets of pre-trained embeddings trained on like all of Wikipedia plus these big like chunks of text from the internet. So notice that some of the words are very similar to what we had before from the ones that I made myself. But we no longer have some of that domain-specific flavor, like clerical discrepancy. And now we have probability, which, people were not talking about that with their financial product complaints. So what we're seeing here is this evidence of how embeddings are trained or learned from a large corpus of text data. So the characteristics of that corpus become part of the embeddings. So, I'm sure you've heard people say before, or you've experienced it yourself, how machine learning just in general is exquisitely sensitive to whatever is in your training data. And I don't know, I think this is maybe never more obvious than when you're dealing with text data. And maybe word embeddings are maybe the easiest example to see this in. So any flavor, any like domain specific context, any human prejudice or bias in the corpus becomes imprinted into the embeddings. Um, in fact, when we look at some of the most commonly available embeddings, we find that by that like in this new space that we make, African American first names are associated with more unpleasant feelings than European American first names. Women's first names are more associated with family. Men's first names are more associated with career. And terms associated with women are more associated with the arts, and terms associated with men are more associated with science. So, in fact, bias is so ingrained in what word embeddings are like that they can be used to quantify change in social attitudes over time. So researchers have measured have measured the bias in word embeddings over time and use it actually to quantify changes in social attitudes. Which, when I learned that, I was like, whoa, like this really tells you what word embeddings are like, right? So word embeddings are, maybe a pretty exaggerated or extreme example, but it turns out all the feature engineering decisions we make when it comes to text data have a big effect on our results, both in terms of model performance, but also in terms of how appropriate or fair our models are. So with all that we've said here, like when it comes to pre-processing your text data, creating these features that you want to use as inputs for some kind of model, you have a lot of options, and I think quite a bit of responsibility. So my advice, if it's time for you to train a text model, is to start with simpler models so that you can understand quite deeply. To adopt good statistical practices as you train and tune models, so you aren't fooled about model performance you might expect to see with various approaches. Let's say you start trying more complex models, and also to use model explainability tools and frameworks so you can understand your less straightforward models as well as you can. So my coworkers and I have written about all of these and like how to integrate your modeling with all these things I've talked about, and is a high priority for us moving forward. So with that, I will say thank you so much. I want to be sure to thank my teammates on the Tidy Models team at RStudio, including Emil, who is here, my co-author on this book.